Alright, we're going to prove a result here about cyclic groups. And the result is going to be basically be able to tell us at the end that every subgroup of a cyclic group is itself a cyclic group. So let's take a look. So we have a cyclic group generated by some element g. Let's go back here. I'm going to let subgroup. And I'm going to let g of m be the smallest. M is the smallest positive integer for which it's true. So every element of G, so every element of H, has the form G to the M. And I'm going to pick M to be the smallest power that is in H. And then that H is equal to, H is generated by G to the M. And for every integer, G to the K is in H if and only if M divides K. So, in other words, M is going to be the smallest power that's in H, and then everything else is going to be multiple of M. That's in H. And first of all, we're going to prove the last part, that G to the K is in H if and only if M divides K. So let's assume that M divides K. Well, then what I can do is, by definition of M divides K, I can write it as QM for some integer Q. That's what it means for M to divide K. Just like 2 divides 6 because 6 is equal to 2 times some integer. And so we're using that. Then K is equal to, just by using laws of exponents, is just going to be Q copies of G to the M using laws of exponents. What does that tell me? So G to the K is just a power of G to the M, and G to the M is in H. H is closed, so if I take a bunch of G to the M's and got Q of them, I'm going to stay in H. So that tells me that G to the K is in H, which is half of what I needed. Now I need to prove that that if G to the K is in H, then M is going to. So I'm going to assume this is in here. I'm going to show that that K is a multiple of M. What I can do is use the division algorithm, which says that I can find integers Q and R for quotient and remainder. And R is going to be between 0 and M. And what I can do is I can write G to the K as just two things, right? I've got a bunch of powers of G to the M and times the lone G to the R. And then what I can do is I can solve for this G to the R. G to the R equals that. But look at this. Here I have G to the M, and G to the M is an element of H. So Q copies of it are S and H, and since H is a subgroup, it's closed under inverses. So therefore, this whole thing is in H here. This whole thing is in H, but also G to the K is in H as well, because I'm assuming that. So what does that get us? That gets us that that's in H. So what I'm going to use now is that M is the smallest integer that is in, such that G to the M is in H. And R is less than M is the smallest integer, and R is between 0 and L. So that means that M has 0, because R can't be positive. If R were positive, it would be less than M, and that would contradict the definition that M is the smallest positive integer. So we conclude that R is 0. But what is that? That means that K is equal to QM plus R, which is QM, and that means that, in fact, a multiple of M. In other words, M divides K. All right, we're almost done. So now we're going to prove that H is generated by G to the M. Look, by closure of H, certainly the subgroup generated by G to the M is in H. Great, so I just name it now. And so I'm going to let H be any element of H. And I'm going to show that it's actually a power of G to the M. Well, what do I know? I know that the original group G is cyclic. The G that I'm in is cyclic, and it's generated by G. So this H has to be equal to a power of this G, because everything in capital G is a power of G, or little g. So I can say that H is equal to G to the K for some integer K. And we prove that such K has to be a multiple of M. So that means that G to the K is equal to G to the M to the Q, which belongs to subgroup generated by G to the M. So we get that. means that H is contained in there, and we conclude that we get equality. And that's it, we're done. We proved what we And the corollary is that all subgroups of cyclic groups are cyclic. Why is that? Because we proved that every H has that form. That's all.